All right, so we just spent quite a bit of time working on how to take nth roots of 1. And now we're going to return to looking at nth roots of general complex numbers. So if you have, so in general now, if you have some complex number a, which is in C, then if you were to draw it, let me even, let's say a is in C. If we were to draw it, a has some, a is somewhere here. Let's say it's over here. And if we were to draw the ray here, that has some length r, and this makes some angle theta with the positive real axis. The sort of principal value of the nth root of a, if you've done some complex analysis stuff, let's set alpha. Well, okay, let me say one more thing first, sorry. We know from polar coordinates that a is re to the I theta, okay, because that's just cosine plus I sine, and that's just saying a is r cosine plus r sine, or r cosine comma r sine. So then the sort of starting nth root, which I'm going to call alpha, which is the nth root of a, is really going to be the nth root of r e to the I theta over n. Okay, so this is sort of like a definition of the nth root. So you take the nth root of the length, the distance to 0, or the length of the complex number, and you divide the angle by n. So if we were to visualize it, it would be like here. This would be like our alpha. If sort of n was 3, if n was like 3, we would maybe, for this example, if n was like 3, this would chop it in thirds. Okay, that's a third. And then I take like a cube root of that. Okay, so this would be, as an example, like a cube root of a. Okay, so that is sort of one root. And it's really easy to check that this is an nth root. So it justifies this notation. Namely, alpha to the n is the nth root of r, e to the I theta over n to the n. And this is the nth root of r to the n, which is r, and e to the I theta over n. You multiply them, so you get e to the I theta, and that's a. So alpha to the nth power is a. So that's good. Let me use gold. Great. So that's one root. What are the others? Well, let's let, again, zeta n equals e to the 2 pi I over n be the standard primitive nth root of unity. It doesn't matter that it's the standard one. You can take any primitive nth root of unity, and you could do exactly what I'm going to say, but it's somehow psychologically more comforting for me to have one chosen. Then all n of the nth roots of a are, well, there's alpha, there's zeta n alpha, there's zeta n squared alpha, and you keep going till you get to the n minus first power times alpha. And that's what they are. Those are all the nth roots of a. Let's check real quick. What's the check? Well, they're all different because all of the zetas are different. So they're all distinct. Distinct. And let's check that they're nth roots. So what does a general element here look like? It looks like zeta sub n to a power times alpha, sorry. And we have to check that when we raise that to the nth power, we get a. Keep in mind, alpha to the nth power is a. All right, so what's this going to be? Well, it's going to be zeta sub n to the k to the n, and then alpha to the n. But zeta sub n to the k is an nth root of 1. It doesn't matter if it's primitive or not. It's an nth root of 1, so we get 1. And alpha to the n is a, so we get a. So we have n distinct complex numbers that all, when we raise them to the nth power, we get a. So this is all n of them. We have all of them. So let's do a quick example. And then this is a formula that we just use, and the more you use it, the more used to it you're going to get. So as a quick example, let's look at the fourth roots of -1. Okay? Fourth roots of -1. The rule was we first need to find one root of -1. In polar form, -1 is a distance. Let me say polar form first. Well, this is like polar exponential form. I'm not even going to name it. The distance that -1 is to the origin is 1, so our r here is 1. And the angle that -1 makes with the positive real axis, -1 is on the negative real axis, is pi. So this is the same as -1. And this is the most beautiful formula, right? E to the I pi is -1. So one of our fourth roots is going to be take the real fourth root of 1 and then e to the I pi over 4. The real fourth root of 1 is 1, so we just get e to the I pi over 4. Which if we wanted to, we could write out as cosine pi over 4 plus I sine pi over 4, which if we wanted to, we could compute as root 2 over 2 plus I root 2 over 2. And if you sit there and you take that binomial expression to the fourth power, you indeed do get -1 when you do that. Okay. All right, so that is our alpha in this case, and we actually already computed the fourth roots of unity. Let's go and look at them real quick, just to remind ourselves. When n is 4, the primitive fourth roots of unity are I and -I, but the standard one is I. The second power is -1, and the third is -I. So what we're going to do is we're going to multiply alpha with all fourth roots of unity. And I'm going to multiply the binomial expression on the right. The first root of unity is 1, so we get 1 alpha, which is alpha. And then we have I alpha. If we multiply this, I was the standard primitive fourth root. If we multiply that expression with I, what are we going to get? We're going to get I times root 2 over 2 plus I root 2 over 2. That's going to give us an I root 2, and then we're going to have an I squared. So we're going to get negative root 2 over 2 plus I root 2 over 2. Cool. And then we have to multiply -1 with alpha. We get negative alpha, so that's negative root 2 over 2 minus I root 2 over 2. Cool. And then we have to multiply it with alpha with negative I alpha. Well, we already did alpha with I, that's here. So we're just going to negate it, and that will give us the answer. So we get root 2 over 2 minus I root 2 over 2. And let's take a moment and let's just look at the fruits of our labor real quick. Let me draw the unit circle. All right, alpha is here in green. That's root 2 over 2 plus I root 2 over 2. Let's look at I alpha. I alpha is negative root 2 over 2 plus I. Here's negative I, or here's I alpha rather. It's right here. All right, negative alpha is just look at the other side. So negative alpha is here, and then negative I alpha is there. So it's like we took those fourth roots of unity on the unit circle and we sort of rotated them by pi over 4. And that's, in fact, exactly what happens when you multiply by alpha. But nevertheless, these are the fourth roots of -1. And later, much later in the course, I think even in the last chapter, you're going to return to the fourth roots of -1. And you're going to compute the Galois group of it. And I'm going to go back and I'm going to remind you of this, that we actually did work out all the roots and they're here.